Hi, I'm Bryan Woodbury, and I'll be presenting our FANUC RC Painter robotics project. This is a four-person team project for a robotics and automation class here at Eastern. I took that class last winter. And our task was to design and construct and program a fully automated system. We had our choice of robots, and we chose to demonstrate the flexibility of a 6-axis spherically articulated robot arm. We also had to design and build an automated system to support the robot. We used the FANUC LR-Mate 200IB industrial tabletop robot. It's a 6-axis spherically articulated robot arm with human-like motion and reach. Our mission was to paint RC car bodies for remote control cars, and there are a number of challenges we had with that. One was the short arm reach of the robot arm when we tried to paint the outside of the cars. Another was that there are various styles of cars that we chose to increase our challenge. So instead of just one particular pickup truck or something, we chose I think 5 different car models. The car bodies were very lightweight. They're only ½ an ounce each. They're transparent and they are non-metallic. So the solutions to those challenges were that one, that we found a common factor between all the parts, and that was in the corners. These are formed plastic pieces, and some of the car bodies were up against one side or another. And they're all different shapes, but the common factor is that all the corners were practically the same. So another thing is we decided to paint the inside of the cars. We found out that RC car bodies are ideally painted on the inside to protect the paint from scratches and to give the paint a nice glossy shine, just like a clear coat on a car. Also, we had a wide variety of sensors to choose from. So this car is a McLaren F1. That was my favorite. This is our gripper assembly. This is made from sheet metal, and see, that's all sheet metal there. And then these corners here are made of UHMW. That's ultra high molecular weight polyethylene. And we cut little beveled corners into these pieces to automatically center the parts as we closed in on it with the gripper. That's passive compliance. So whether the part was a little too high or too low or off center, a little bit rotated or anything, as the gripper closed, it would automatically center it. Take that into account. Here's an overview of our workspace. You can see some of the conveyor system here, and obviously the robot arm sensor over here, and this is our gripper picking up a car here. This is our spray tower. Here's a step back looking at the full conveyor system, a car in the hopper down there, and this is a car body actually being painted here. This is our spraying process. So we're spraying the inside of the car bodies, and we built a spray support tower here out of wood. This is our airbrush sprayer and the pressure regulator. So when you turn on the sprayer, it would spray here, and the arm would move the car back and forth in various motions to evenly spray paint the inside of the car and not stay in any one spot for too long, because that would cause drips. And you can see the end of the conveyor here. They fall off the edge into a part holder and the sensor over there. When the car is done being painted, we bring it over here off to the side, and there's a paint curing conveyor for the final step, and that's where they finish off our project. Here's a photo of it in action. You can see the gripper passive compliance pieces here. This is a pneumatic parallel gripper here, and this is the paint curing conveyor where the finished cars straddle a paint curing light here to simulate like to help the paint cure faster. This is our main conveyor system. It's made of a bicycle inner tube and a DC gate motor to turn it. And it didn't have quite enough friction, so we added beads of RTD silicone here, which gave it just enough friction to move the cars along consistently. This is our DC power supply. We used 1/2 of it here, fine-tuning the voltage and current to set the speed and torque of our conveyor. This is powering our DC gate motor. And this is the pickup tray, another angle of that. So when the parts fall off the end here, they stop there at the bottom. These aluminum guides keep the cars straight the whole time. There are guides down both sides. It is pretty critical to keep the speed just right, the speed and the torque of the conveyor, because if the car is going too slow over here, it wouldn't have enough momentum to actually fall down. The friction would stop it part way and we'd have an issue. If the motor is going too fast, we would have issues with with one car piling into the next, because it takes a little bit of time for the motor to stop turning. This is our spray tower here. The airbrush sprayer is held on continuously. This air pressure regulator is set to 10 psi. It doesn't take very much. The robot has 2 internal pneumatic solenoid valves that we use to turn the air pressure on and off with our program. So one of them would supply air to this whole system. The other valve was used to open and close the pneumatic gripper. You can see here in this angle, these notches here, that's where the gripper fingers come in on the sides. This is the ultrasonic sensor. We had a number of different sensors to choose from, but most of them don't work for this application because the infrared sensors would pass the light through the transparent plastic. An inductive sensor wouldn't work because they're non-metallic. Capacitive sensor wouldn't work very well because it needs to be pretty close to the part, so it could be in the way of the gripper, and it would also be in the mist cloud of the paint. And they're very lightweight. They only weigh 1/2 ounce each. So if we use a spring-loaded limit switch, they could bump the part out of alignment. So we don't want that. So we use this ultrasonic sensor. It bounces sound waves off the plastic. Our plastic parts are rigid enough with all the bends and contours to it, so it would actually reflect the sound back. And it didn't matter if they're transparent at a long distance, so good sensing range. Just a good choice for this application. And then over here, this is the aluminum guides here in the part pickup tray. And what I did is I used open cell foam on the side of that to absorb the sound waves. Otherwise, they would reflect the sound back and it would detect a part even when there isn't one there. So this sensor detects the car and starts and stops the conveyor. This is our control relay here. It's normally closed. So normally it's running the conveyor. As soon as a part is detected, it would stop the conveyor. And then as soon as we pick up the car, it would resume operation. So it doesn't matter if you have the cars right next to each other or one part coming down the line every 5 minutes. It would just work continuously. And here's an overview of the whole system. And I have a short video to show you. I'm just going to kind of skip through it a bit here. You can see it in action. That's the motion of the paint spraying to get all the two sides, the front, the back, and the top. It sets it down there on the conveyor. Now it picks it up. Doesn't need very much motion on the gripper. This is the solenoid opening and closing. a couple different angles of the conveyor and the ultrasonic sensor. That's a paint curing conveyor. Uses a disco ball motor to turn very slowly at just 2 RPMs. And here's the whole process. All right. Any questions?
Bryan, what was the object of this exercise? Just to give you guys practice in setting up a production line?
Yeah, basically just to learn about robotics and automation. Our task was to impress the instructor, our director. We could do basically anything we wanted, so we just decided on a challenge and went for it. Yeah.
So with this, that was basically set up to paint the entire inside one color.
Right.
Could you set that up? I noticed that it had like windows, rail posts. Could you set it up to actually paint on those individual pieces without painting the entire inside?
It'd be hard to actually paint those. I think normally those are like black stickers and stuff that they would get put on before the car got painted. Yeah. It'd be like a hand operation to do something that precise.
Did you actually paint any cars, or?
We started to, and we had a plan for extracting the fumes, but one issue is that if we use the vacuum line that are supplied in the lab, then all the fumes would end up in a closed room with a vacuum pump down in the basement, so that wasn't good. And the other thought we had was to just run a pump and pump the air out through a hose, like a dryer hose, and out the door, but that would be running through the CEB lobby and out the door, and that would get stepped on and have the door closed on it. We just decided it was just so stinky that we would just simulate it.
Would it have bad to paint the FANUC anyway, somebody would be angry with that?
Yeah. We did have it all wrapped up before when we did test it, so. And then we peeled it all up because it looked better without the cover. Yeah.
So if you were to apply this in industry, how would you deal with overspray issues?
You'd just cover everything up and not use any more pressure than you have to. Make sure you keep the car no further than it has to be. But basically just covering everything up really well. Yeah.
Were there any problems that you ran into that were really hard to diagnose? When you got like a prototype put together and tried it out for the first time?
There were a number of problems. One that I remember was the alignment of the ultrasonic sensor, because we had to get the height just right and also the angle, because sometimes we're bouncing off the hood of a car, sometimes off the trunk, and the Acura NSX versus the McLaren or the Porsche, they all have different angles, so that was pretty tricky, but we have just trial and error, we found one that worked. Position. Yeah.
Did you guys decide to go with the ultrasonic sensor before you set it up, or was that kind of like a trial and error thing because other sensors weren't working for you?
No, we didn't bother trying any of the other sensors because we knew what their fallbacks were, drawbacks.
All right.
Thank you very much.